Algebra 2, Chapter 7, Section 6. So we're going to look at solving exponential functions and log functions. Just reminders, the log base b of 1 we should know is 0, log base b of b is 1. We keep reviewing these, you should know these by now. We should also know the change of base formula. That'll help us evaluate some of these by calculator to have approximate decimal values. So our goal, again, is to solve exponential and log functions. We have some basic equalities we should know here, is that if we have a to the x power, and that equals a to the y power, if they have the same base and different exponents, those exponents actually have to be the same. So the only way that's going to be true is if those two exponents are equivalent. The same thing is true with our logs. Log base a of x and log base a of y, same bases, x and y would have to be the same. It's the only way if that's true. So this is called one-to-one property. This is called the one-to-one property. Because both sides have that same base. So the exponents here, or the x and y here, need to be equivalent. So to set these up, to solve these, since we have base e for this example, base e, since both sides have base e, there's only a single term and a single term here, then the exponents have to be equivalent. The only way for this to be a true equation is if 5x plus 2 has to equal the other exponent, 3x plus 12. And then we can solve this out by normal, subtracting 3x to both sides, subtract 2 to both sides, divide by 2 to find x is 5. And then we can back substitute to make sure that's correct. And you get 27, so e to the 27th, and then 15 plus 12, e to the 27th. So it works out. And so this is called a one-to-one property. Sometimes when you look at the problems, it's not set up in one-to-one, but we can make it one-to-one. So like this example here, we have 8 to the x minus 1 power, and 1/2 to the 2x minus 1 power. Now can we rewrite these so they have the same base? And so I think about how 8 I could write as 2 to the third power, and then that third power is to the x minus 1 power, which is I multiply that. So I get 3x minus 3. We do the same thing. 8 to the x minus 1 power is the same thing as 2 to the 3x minus 3 power. And then this 1/2 to 2x minus 1, I can rewrite that 1/2 as 2 to the negative 1 power, and then distribute that negative 1 through this parenthesis to get 2 to the negative 2x plus 1. And so that would be equivalent. Now it would be one-to-one properties. Now we both have base 2, so I can say 3x minus 3 has to equal negative 2x plus 1. We can solve that. We can add 2x to both sides with 5x. Add 3 to 4, so x has to be 4/5. And the last one down here, same thing, this would be 9 to the 2x power. I'm going to leave that. But 81 could be 9 squared. And that 2 gets multiplied through that parenthesis to get 6x minus 4. And so then 2x has to equal 6x minus 4. And then we can solve that, so subtract by 6x, divide by it, so you should find x is 1 when you solve that. So this is called the one-to-one property. If you make the bases the same, then it's going to be a similar solving. To solve, we're using the same steps. We can, one, rewrite the original equation in a format that allows the one-to-one property. That's really type 1. Type 2 is really referring to this, which is apply the inverse property to isolate the variable. So remember that if we have a to the log base a of x, that's just x. And we have log base a of a to the x, that's just x. And so we can look at this, is that this is 4 to the x power. So what's the inverse of that? It would be having both sides be log base 4 and log base 4. So if you do that to both sides, log base 4 of 4 to the x power is just x. That's going to equal log base 4 of 40. And then you can use change of base to actually evaluate that. Another way to look at this problem is if you take the original problem and put it in an exponential form. That's going to be, our base does not stay the same, so it'll be log of our base 4, and then the x and the 40 change spots. And so that's the other way to still get the same setup. But we do need to put this in the change of base. So that's going to be log base 10 of 40 over log base 10 of 4, and then approximate that in the calculator. Similarly, here we can say this is base 7, so we can do like log base 7 and log base 7 to both sides. And then you get the exponent x minus 5 equals log base 7 of 200. Then we still need to add both sides by 5. So x is going to be change of base, do the natural log of 200 over natural log 7 plus 5. Added 5 to both sides to isolate my x. So this is what I punch in the calculator to find the approximate value. The last one down here, we want to first isolate our power. So we have this 3 in front. I want to divide both sides by 3 first to get 5. And then the inverse of having the base e would be log base e, which is just the natural log. So we're going to do natural log of both sides. And so we get 3 minus x equals the natural log 5. And so for me, I would add x and then subtract the natural log 5. So x is going to be 3 minus the natural log 5. And you can punch that in the calculator to find the approximate value. Type 3, now we have, these are logs. So they start off with a log. So it's the inverse of that. Instead of having log base 7, I would want to raise or have both sides have a base of 7. So I make both sides be actual exponents. So 7 to the power of log base 7 and 7 squared. So then I can write that as x plus 3 is equal to 7 squared, which is 49. Subtract 3 to both sides and get 46. The other option here is to actually put it into exponential form. That's another method of doing this problem. And to do that, our base is 7, so 7 squared equals x plus 3. And then I can solve it the same way. 49 minus 3, I'm still at 46. I tend to teach students using the inverse. I want you to become familiar with that and accustomed to that. Putting it in the opposite form, exponential log, is another technique that will help you out though. So here we have natural log 5x equals 9. The inverse of that, this is log base e, that's what natural log represents again, so log base e. So I'm going to have both sides have a base of e. So now I have e to the natural log of 5x, which is just 5x. That's going to equal e to the 9th power. I can divide both sides by 5, so x is going to equal e to the 9th power divided by 5. And again, you can approximate that in the calculator just by punching it in. I'm just going to keep it exact. So this is really how to solve. So here's what's a little different. For this one here, now we're dealing with a log plus another log. So now we have more than one log in the problem. When that occurs, we're not going to solve it like we typically can. We can't just have both sides raised, have the base 10 to both sides. We got to first condense this. We have to write this with one log first. And so since we're adding here, we're going to condense that. They both have base 10, so we're allowed to condense that. We're going to get log base 10 of 2x times x minus 5 equals 2. So that's condensing. Then I'm going to have both sides have base 10, because that's going to be the inverse of having log base 10 there. So then I get 2x times x minus 5, which I would multiply through to get 2x squared minus 10x equals 10 squared, which is 100. I would then divide, either way, divide by 2. X squared minus 5x equals 50. Subtract the 50, so x squared minus 5x minus 50 equals 0. Now that we have it equal to 0, we can then solve this. I would solve by factoring, so this will be x minus 10 and x plus 5. So notice our quadratic knowledge comes back into play here, and we get 10 and negative 5. And then we could plug them back in to look for extreme solutions, just like we did for previous chapter in radical functions. We had to do the same thing here to make sure that we don't have extreme solutions. So we plug in a 10 here, log base 10 of 20 plus log base 10 of 5. I can evaluate all that, but we plug in a negative here. we're getting log base 10 of 2 times negative 5. Let's look at just that portion. We'd add more, but this is log base 10 of negative 10. Well, let's put this into, let's make this equal to some value we'll call m. Let's put this into exponential form. This is 10 to m equals negative 10. Is there any exponent that will give us a negative value? If we make m be a negative, it doesn't make it become negative, it makes it become a fraction. So this is not possible. We can't have 10 to some power and become a negative value. So we cannot take the log of a negative, log base anything to a negative value. So negative 5 is actually not a possible solution. So then x has to be 10 is the only solution for this problem. So be careful when you get values. Plug them back in to see, are you only taking a log of positives or a log of negative? You plug it in to create a log of any base of a negative, but it's not going to be a solution. So this is another way you can actually find the solution of that same equation. Here's that same equation we were dealing with, really. Because if you look at the previous problem, here's the equation, and we want to know where it equals to. So another way to actually find that is we can actually put in this graph. So this red equation is the log graph right here. And then we're setting it equal to 2. We're trying to figure out what's 2. So if we plug in that equation, y equals 2, it's this horizontal line. And so we're trying to figure out where those two are intersecting. There's a feature on your calculator that will actually do that. It's the same spot where you find max and mins. You can see here intersection. Here's an application problem. Kind of goes back to the beginning of our PERT or compound interest. So unless you deposit $500 into an account that pays 3.25% annual interest compound monthly, how long does it take for the balance to quadruple? So quadruple is 4 times, which really makes the amount I'm putting in irrelevant. If I look at the formula, the amount of money I have is the principal times 1 plus r over n to the nt power. If I put in some p amount and I want to quadruple, the a amount's got to be 4 times as much. So if I divide a divided by p, it's always going to be the amount I want it to grow by. So like 4 times or 5 times or double or triple or whatever it may be. So a divided by p would always be that amount. So I would just put 4 equals, and then I'd plug in 1 plus the rest of it. You could plug in, like, okay, 500 is what I'd plug in. If I quadruple that 5 times, 4, we have 2,000 here. Then divide by, you'll still get the same value, 4. And so when you plug in our R value, 0.0325, compound monthly, so that's 12 times in a year, to be 12 times, and then we do not know our time. That's what we're trying to solve for. How long? T, don't know that. So let's solve for that. And so that's our exponent. Our exponent really is not just t, it's 12t. So our base is this mess right here. So to isolate this exponent, I need to do log base, whatever this junk is, to both sides. Another way to think about it is I could put it into into log form. It's going to be a log of the base, 1 plus 0.0325 over 12. So log of the base of 4, log base, that junk of 4, is going to equal my power 12t. And then to solve for t, we're going to divide both sides by 12. So to find t, we have to first figure out the log of this and then divide by 12, which it's not too bad. It's just a lot of decimals here to punch in. We gotta use change of base here. And so if you're gonna evaluate this in the calculator, I need to actually punch in, I would do natural log 4 over natural log of that parenthesis 1 plus, be careful how you punch this in, make sure you keep your order operations. So that's a change of base. And then I take this answer and I want to divide that by 12. So that's what you want to calculate. Try plugging it in. I don't have my calculator on me. You can give that a shot and see what the time is. That's how you plug it in. So here is one more problem. So there is your video problem for the night, and we'll see you tomorrow.